Well, welcome to the first talk in our guest speaker series. Today we have David Bailey, who will give a talk about experimental mathematics, serious research, and great fun. So take it away.
Very good, thank you. So what we're talking about here, experimental mathematics is really just a fancy term for using computers as part of mathematical research. And really all historical mathematicians, including our friend Euler pictured here, used experimental method. They always worked out examples. They did numerical and symbolic manipulations and to try to get insight into intuition. There's really nothing new here. It's just what's new is that we have much more powerful computer-based tools nowadays. I might just mention here that one thing that is new, especially, is that we have computer tools now that can actually discover new identities and other mathematical facts. And then there's, with some additional effort, actually provide some help in trying to define proofs for discovered facts. And again, we have to put this disclaimer here, although the computer-based tools are very useful in mathematical exploration, we still have to prove things the old-fashioned way. There. One thing I think that's very refreshing is that experimental math, from my experience with it, is really quite an interdisciplinary endeavor. I have personally worked with pure mathematicians, applied mathematicians, physicists, all of these listed here. A lot of people can make contributions here. And yes, at all different levels. And I list here down to high school students with good math and computer programming skills. I personally worked in several cases with students, including a former TA of Euler Circle, who have made significant contributions, both in the mathematics and in the computing. Okay, so here's just some tools that we use. Of course, many of you are familiar with this Mathematica and Maple, and also this Sage that's open source. You might not be familiar, there's something called the Online Encyclopedia of Integer Sequences. You can look up a sequence of integers that say you get when you're doing some derivation and see if it's a known sequence. Very likely it will be, and it'll tell you what papers that are that actually produce it. Another thing that's called the inverse symbolic calculator, where you enter in a numerical value, like a number to 30 digits accuracy, and it'll tell you if that's given by some formula. And then, of course, there are things like high precision arithmetic software. I've written some of this package myself. That's very useful, particularly, as we'll see in a minute, like high precision numerical integration, and then especially integer relation detection is very important, as we'll see in a minute here. So what I'm going to do today is just give a brief tour of what we call experimental mathematics. And I'm going to give you some examples of real state-of-the-art work, but I've selected cases that are really rooted in very basic concepts that I think most of you would be able to at least follow at least the statement of the problem and get a flavor of what we're doing. But again, I have to say, many details are skipped. If you'd like to pursue any of these, either send me a mail or just look at the references in orange. I might just mention, again, you look at the bottom there, you can actually download this talk file, and it'll include the references if you'd like to look anything up. And so anyway, here's just one example, a very interesting problem of normal numbers. A number is said to be normal, say in a given number base, if basically every string of digits appears in the expansion with the limiting frequency you would expect at random. And so you might say, oh, like with every, if we're thinking base 10, you'd say every 3 appears in the limit 1/10 of the time. And the string 3/7 appears in the limit 1/100th of the time. And the string 3/7/2 appears in the limit 1/1000th of the time, etc. And for every other combination of any length. Now, you might think with all of that condition, are there any normal numbers? But we can show through measure theory that actually, in the measure theory sense, almost all numbers are normal, base B for any B or for all B's together. But it's a curious fact, it's very hard to list any number, particular number that's provably normal. Here's one that is provably normal base 2, in other words, or base 16 equivalently. In other words, the base 16 digits shown there, or you can show are provably normal in this sense. If you look at the papers below there, if you'd like to get the details. So here, one very interesting question, is pi a normal number, for instance? And computational experimentation have never found any reason to question whether it is, but it's there's no proof, not for any number base for pi. And what's more, it's basically the same situation for almost any other common constants of mathematics. In fact, we can make a conjecture that not only is like the square root of 2 normal base B for any B, but any algebraic number is normal, again, in any number base. But again, we have not proven that for any specific algebraic number or any particular base. So there's a lot to be done here. Here's just an interesting example of how we can use graphical tools to explore such questions. This is a random walk. Basically, we start at a given point, and then we go right if the base 4 digit of pi at that position is a 0, up if it's a 1, left if it's a 2, and down if it's a 3. And we just start wandering around the plane here. You can see it starts at red, goes to orange, yellow, green, and then back this way and wandering around. And then we can compare this with say, a truly random walk, and we can see what interests. If you like some details, look at this paper here. Now, there's one very important tool that if you only remember one thing from this talk, remember the PSLQ integer relation algorithm. Basically, if you're given a vector of real numbers, and you can think of these as specified to very high precision numerically, an integer relation algorithm will find integers, if they exist, such that this sum is 0 to within the epsilon of the numeric precision you're using. And so basically what this can be used for is we can discover new, quite possibly unknown mathematical identities based only on the numerical values of the input terms. And but again, the proviso is we have to do these calculations using very high precision, numerical precision. And I mean like hundreds or even some cases thousands of digits to get numerically significant results. This PSLQ is the most widely used algorithm, but some people use this LLL and some others. So how does this work? Basically, given a vector X of real numbers, PSLQ constructs a sequence of matrices such that the matrix product, or the vector matrix product x times b sub n, gets smaller and smaller with larger n, until at one point some entry of y is 0, or down to the epsilon of the numeric precision we're using. There are some variations of PSLQ. Again, if you want details, the second paper is probably the best source here. So here's just an example of a real PSLQ computer run. And this is the smallest of the y vector, the log 10, the base 10 log. And you can see as we're coming along, it's just slowly drifting down to about 10 to the minus 50 or so. And then suddenly at iteration 199, it drops 200 orders of magnitude down to about 10 to the minus 250. And we were using 250-digit arithmetic. So essentially it's found 0. And that the size of that drop, at least is numerical evidence, certainly not rigorous proof, but strong numerical evidence that we really did find a real mathematical relation there, a real mathematical identity. And then we can proceed to try to prove it. Anyway, just a little bit of background here. How many of you are familiar with what's known as the binary algorithm for exponentiation? So all we really mean here, suppose we wanted to compute 3 to the 10th or 3 to the 17th mod 10. In other words, what's the last decimal digit of 3 to the 17th? Well, there are 3 ways of doing this. One is we just literally multiply 3 together 17 times, and we get this value, so the answer is 3. But a faster way that you probably have noticed in some of your work already is that we can just square 3 4 times. So we get, that gets us up to 3 to the 16th, then one more multiplication by 3 and we have our answer. But the fastest of all is, since we're only interested in the final result mod 10, is just we reduce mod 10. In other words, we take the last digit each time we do a square or multiplication. And literally you can do this last line in your head. It's that simple with this scheme. And it doesn't matter if the exponent is very, very large. It's very easy with this algorithm. So what can we do with this? Back in 1996, Peter Borwein, who's a rather distinguished Canadian mathematician, was asking, it says, is there some way that we can calculate, say, the digits of pi or something like that, out beginning at an arbitrary starting point, without having to calculate all of the digits that came before? And he discovered this really very simple little fact here with regard to the constant log 2. Now, log 2 is given by this formula here, very well known since the time of Euler. This is the base 10 value. This is the binary digits of that number. Anyway, but he's noticed that if we just look, if we want the digits beginning at position D, we just we can write that as 2 to the D times log 2 and then take the fractional part. That gives us the binary expansion beginning after position D. And now if we take this formula here, we multiply by 2 to the D, and then we split the sum into k to go 1 to D and D plus 1 to infinity. And then notice that in the first sum here, the numerators are all whole numbers. And since we're only interested in the fractional part when we divide by k, it suffices to just compute that numerator 2 to the D minus k mod k. And we can do that very, very fast with this, with this binary algorithm for exponentiation mentioned on the previous view graph. Anyway, so this really immediately raised the question, is there a similar formula and scheme for doing this trick with pi? And there wasn't any known. They really did a rather thorough search of the literature, and they could not find any formula of this general type that would allow this trick to be done. And so Simon Plouffe used a PSLQ type program and actually discovered this new formula. It was perhaps the first formula of pi that's ever been discovered by a computer program. And indeed, it permits one to compute a string of binary or base 16 digits, beginning at an arbitrary starting position, using a simple algorithm that's very similar to the scheme that we mentioned for log 2. And I mean, you literally, some rather eye-popping calculations have been done just for the heck of it. The 2 quadrillionth binary digit of pi is 0. And there's also implications for the normality of pi that you can read about if you're interested. So this is perhaps the first really big discovery using this PSLQ approach. But since then, many other similar things have been found. Here are some formulas that were literally discovered using PSLQ for like pi squared. And notice there are 2 formulas here. This first formula allows one to compute binary digits of pi squared beginning at an arbitrary starting point. This formula, the second formula, allows you to compute base 3 digits of pi squared beginning at this arbitrary starting point. Here's again a similar formula for pi times log 2, and there are many other examples that have now been found. So here's one other thing. Here's just another common application of this PSLQ algorithm. Suppose we can compute some number. Let's say look at this number alpha. And we suspect that this may be an algebraic number. In other words, it may be the root of a polynomial with integer coefficients. And what is that polynomial? So all you need to do is we just calculate this vector 1 alpha squared up to alpha to the 30, let's say, to high precision. I use 250-digit precision. And then input this to a PSLQ program, and poof, out pops the answer given here. And Mathematica verified, indeed, it is an irreducible polynomial. This is just sort of an example of the sorts of discoveries that we can use. Here's another thing, is that suppose we can numerically calculate some definite integral to high precision, and we suspect it may be given by some nice slick formula. What is that formula? Well, again, we can use PSLQ. The trouble is that computing integrals to very high precision is not easy, or at least it has not really been studied that much in the literature. And most of the common numerical integration techniques, say, that we study in a numerical analysis class, just really don't work, really fall apart when you're trying to do this at high precision. But so here's a very curious but important fact. For a few special functions, typically given by like some kind of a bell shape, such as the Gaussian probability function that you've probably seen, just using a simple block function or the trapezoidal rule approximation works remarkably well. Typically reducing the block size in half doubles the number of correct digits. And so why is that? Why for these special class does just a simple block function approximation work so well? And it turns out to be due what's known as the Euler-Maclaurin summation formula, which I've shown here. And again, it looks kind of complicated at first, but really all it's saying is that if we have a definite integral The first term here is simply the block function approximation. The first and second terms together, that gives us the trapezoidal rule. And then these terms can be thought of as just simply higher order correction terms to the trapezoidal rule. Now, notice in this particular, like for this particular function, has the property that the function itself and all higher derivatives go to zero as you're approaching the endpoints and the derivative, the ends. And if you have, what this formula says is if that's the case, if the function itself is zero at the endpoints, this term goes away. And then all of these terms go away too, because all of the higher order derivatives are zero. And we just get that this simple block function approximation is very, very accurate. So that gives us a very slick way of evaluating integrals, say, of functions like that. But what about all the rest that we might want to do? Well, let's just do a little trick here. I think most of you are familiar with the hyperbolic trig functions. They're really actually just very similar to the normal trigonometric functions, and they even have similar properties for their derivatives. Numerous applications, and especially in applied mathematics. Anyway, here's a very cute scheme. Really was not very well known in the literature until recently. It's called the Tanch-Cinch numerical integration scheme. So basically you just calculate these numbers x and w and xj and wj for some given n and h. And then the approximation to your integral is just given by this simple sum here. That's it. That's the entire algorithm. And yet it just works marvelously well, especially at very, very high precision. And it has this property that if you reduce h, which is the block size, in half, you typically get double the number of correct digits. So if you can compute something to like 10-digit accuracy, you just split h by 2 and you get 20 digits. And then you get 40 digits if you split it again. And it even works well if the function is blowing up at the endpoints. And another big advantage is that although this looks a little complicated here, computing these xj's and wj's is much faster than other known integration schemes. And so you say, well, why does this work so well? And basically the trick is that this substitution here that we use, that converts almost any function f of x into one of these bell-shaped functions for which that Euler-Maclaurin trick works. That's the clue here. And it looks, again, it looks wacky. It is wacky. It's strange, but it works like a charm. Anyway, here are some things we can do. Here are just a few, a fact that was actually discovered by a colleague of my a friend, Jonathan Borwing. So where sinc is sine x over x. This integral is pi over 2. This integral is pi over 2. It keeps going up here all the way up to where we have x over 13 is pi over 2. But once we put in the term sinc of x over 15, suddenly it's not exactly pi over 2. It's a little bit less. And so why does this pattern abruptly change? Again, this is just something that was discovered new computationally and just begs for understanding. And anyways, it turns out Borwing, and actually with the help of his father, they actually got a proof here. I won't go through this, but basically it all hinged on the fact that 1/3 plus 1/5 up to 1/13 is less than 1. But 1/3, but when we add in 1/15, it's greater than 1. And that made the difference in the proof. Here's just another curious example. My colleague Richard Crandall encountered this integral in the analysis of some random walks. And so we calculated that with some effort, had to do some manipulations, but we were able to calculate it using this tanh scheme. And here it is to like about 50 digits. Now here is pi/8 to 50 digits. And notice they agree perfectly out to 42 digits, and then they don't agree. What's going on? And that was after some later research that Richard Crandall finally found that actually what's happening is this integral up here at the top is just the first term of a very rapidly convergent series for pi/8. And again, you can look at the details here. But again, the discovery was initially a numerical discovery with a very sort of unexpected result here. Here are just some other examples. Here are some integrals that arise from mathematical physics. And these are kind of nasty because these are multiple integrals. And so we can use things like the tanh scheme, but like a double integral is typically like 1,000 times more expensive computationally than just a one-dimensional integral. And a 3D integral is 1,000,000 times more expensive, etc. And so studying these multiple dimensional integrals is a real nasty challenge. Anyways, it turns out the C integrals at the top, as it turns out we were able to reduce that to a one-dimensional integral. And we computed this with the tanh scheme, and we found that for large n, these seem to approach a limit. Here is the value, or at least up to 50 digits. And so we tried this inverse symbolic calculator where you paste in a numerical number and it'll tell you if it's something interesting. And bang, the result came back. This is 2e to the minus 2 gamma, where gamma is Euler's constant. And so we later were able to prove this. Really a rather unexpected and an amazing result. So anyway, here are some other results like this that we found using a combination of tanh and PSLQ. And again, you might not be familiar with some of these constants, don't worry about it. But anyway, these were some very demanding, very difficult, both computationally and defined rigorous proofs. But again, if you're interested, we'll show you some of the details. Finally, I'd like to go into a recent project that I did with Richard Crandall and John Borwein. Richard Crandall is kind of an interesting character. He is a close colleague and friend of Steve Jobs, that was the CEO of Apple until he died. And so he actually led a group within Apple Computer that was doing numerical computations for scientific applications. He himself had a computational physics background. Anyway, one day he was trying to get a way to sharpen the images produced like by an iPhone. And he came across that this was given by a two-dimensional Poisson potential function from mathematical physics. And so we wanted to understand this behavior of this function a little bit better. And subsequently, Crandall and John Borwein were able to prove that if the arguments x and y are rational numbers, then phi2 is given by 1 over pi times the natural log of some algebraic number alpha. And in other words, where alpha is algebraic, the root of some polynomial integer coefficients. So for example, if x and y are both 1/4, whoops, alpha is this value here, which happens to be 3 plus the square root of 2, a root of that equation of that polynomial. And when x and y are 1/5, alpha is a root of this polynomial. Very interesting. And so we'd really like to understand this better. And so the problem is, from a sort of a computational math point of view, this function, this formula up here, this converges very, very slowly. You literally have to compute 1,000,000 terms of this to even get 3 or 4 digit accuracy. And so, we can't just, we need hundreds or thousands of digits, maybe many thousands of digits. So how can we do this? Well, my friend John Borwein, he was, as it turns out, see a connection to some previous research he had done with Peter Borwein, his brother, on called theta functions. And he was able to show this formula here, which involves these theta functions. And these theta functions are given by infinite series that converge very, very rapidly. Notice this number q here is about 0.04, and we're like raising q to the k² power. So these series converge very, very rapidly. And this allows us to calculate the value of this function to very high precision, literally to thousands of digits if we need. So again, we used this scheme and we did some initial calculations. And here are just sort of a few of the initial results. Again, just in the special cases where x and y are equal and they're just equal to 1 over some integer, very simple sort of case. And here are some of the polynomials that we found computationally. So it really raises the question, what's the connection between x and y and the degree of alpha? There doesn't seem to be any obvious rule, but there's something very interesting going on here. Also, notice the following. Look here at 8. The polynomial for 8, the coefficients read the same backwards as they do forwards. Isn't that interesting? And the same thing is true for 10. The polynomials read just the same backwards as they do forward. We call that a palindromic polynomial. And so does this pattern hold for larger s? And so we geared it up to really do some very much more substantial computations. Anyway, based on just these initial results here and a few others, there's a student at University of Newcastle observed, and again, I have no idea how he intuitively saw this rule. It's strange. And how he intuitively came across this, I do not know. But anyway, this was his rule that would give the degree of the polynomial, at least for the case where x and y are both just the reciprocal of an integer. And anyway, he observed that this rule held for all of the computational results that we had so far, up to about s equal 20. And so anyway, later, after we had done a lot of more research, another student, a student at UC Berkeley, was actually able to prove that this rule holds. for this specific special case, x equal y equal 1 over s. And it's also able to prove that that palindromic property holds when s is an even integer. Anyway, so still raises the question, does this formula hold for other rationals other than this one special case? So this, it turned out, required an awful lot more computation. Basically, here's the high-level algorithm. We use these formulas to calculate phi2, and then this gives us by inverting this, we get our alpha. And then we calculate this vector up for some m, which we just guess. And we apply this PSLQ algorithm to try to find an integer relation, which will give us the polynomial. And if we can't find a numerically significant result, we try again, we increase m, or we increase the precision until we finally find something. Program really requires an awful lot of computer code, but was doable. Anyway, just want to mention here, when I was giving some initial results of this at a West Coast number theory meeting, and Simon was there too, Nityamani, who was a former, at the time was an Euler Circle TA, she pointed out that if alpha satisfies a palindromic polynomial, then beta, which is alpha plus 1 over alpha, will satisfy a polynomial of half the degree. And we can also recover the original polynomial from the half degree polynomial. And it's that since the cost of performing this PSLQ algorithm increases very rapidly with large M, by using this fact, this dramatically reduced the cost for handling the even case. And so particularly when S is an even integer, we're able to do these computations much faster by using Nityamani's trick. Anyway, here's just one example of an example. This is the case where X and Y are both 1 over 23. And this is the polynomial, the minimal polynomial satisfied by alpha. And yes, our computer codes discovered this entire set of coefficients. And so one question that might come up is how do we know that that's really the correct? I mean, there are many thousands of lines of code. How do we know that all that software worked correctly? As it turns out, the fact that it starts with a coefficient of 1 and it goes up in a crescent shape and ends back down with almost a coefficient of 1. This crescent shape turns out is a very strong numerical evidence that all the software worked correctly. And this really is the true mathematical polynomial for this case. Otherwise, if there were bugs, what you would see is all of the coefficients would be nearly the same size. And that's clearly not the case. So again, it's just one of many validity checks we can use along the way to ensure that we really are computationally finding something that really is mathematically real. Anyway, here are just a few of the examples that we found. These are the degrees of minimal polynomials for different cases.
There's a question.
Yeah, please.
Considering that this is for x equals y equals 1 over 23, is there a reason why the first coefficient is 1 and the last is 23, or is that just coincidence?
I think that always happens in the case where the denominator is an odd prime number, at least. I'd have to look at the results, but yes, that kind of pattern always holds. If it is an even digit, it starts at 1 and ends at 1 every time. Again, it has to, because it's a palindromic polynomial. It's proven now to be a palindromic polynomial.
Thank you.
Answer the question?
Yep.
Good. Okay. Here are just some of these. Again, this is computational results. We're turning, again, a mathematical problem into an empirical problem like we study in physics or chemistry. But notice here, many of these results are not consistent with Kimberly's formula. So these are where we have the case x is the reciprocal of an integer, but y is some other fraction. And in those cases, then we don't get Kimberly's formula here would be the case for 1. And so Kimberly would say 128, but here we oscillate between 128 and 256 all the way. But that's not the whole story. Or like here, for 33, Kimberly's formula tells us 240. But notice, boom, all of a sudden out here when Q is 10, it's 120. And again, or look at 36 here. We have some exceptions. So we really don't know yet what's going on here. This is really a work in progress. And in fact, as we talk here, my trusty Mac Studio that I just bought from Apple is hard at work. All 10 processors are full bore computing to find, right now they're working on the case when S is 31, and for all of the fractional cases where the denominator is 31. And so anyway, this is just, it's very much the flavor of what experimental mathematics is. We're exploring the function of what appears to be a very interesting mathematical object, namely this phi2 function. And we don't yet have all the answers. We have some partial results, like this Kimberly's formula and Watson's lad's proof for the special case, but there are other cases we don't understand very well. And this is requiring huge amounts of computation, but hey, what are computers good for anyway? If not to resolve mathematical questions. There's still a lot to be learned. For instance, just as one thing, all of this work so far has been in the two-dimensional case, where we have two variables, an x and a y. What about 3? Again, what we need is some equivalent of John Borweing's special select formula for rapid computation, and we don't have that. So there's still a lot to be done here. And again, if any of you are interested, you can look at this paper here or send me an email. I'd be happy to discuss it with you. Anyway, that's my talk. Thank you.
Good. So let's all thank David for a great talk. Yeah. So yeah, now is a great time to ask questions.
You can probably see them better than I can.
Anyone have any questions for David?
Do you have one?
Okay, so a few people started asking some questions. So someone asked, how do we experiment with experimental mathematics?
Well, I don't quite know what that means, but Basically, there are many different types of experiments that you can run. We can do both symbolic computations. We can look at special cases. We can try varying the assumptions, and it all boils down to trying a lot of specific special cases and seeing if we can see some common rules and commonalities. And once we see those patterns, we can then test them. Like one of the things that mentioned here that, let me go back to this one of his first slides. Testing and falsifying conjectures is a big part of this, because a lot of times you get some idea, some conjecture, but if rather than waste a lot of time trying to prove something, let's test it out first, and this can really save a lot of time. But you maybe do some more tests and trying some more general examples, and we see that it really doesn't hold at all. This was John Borwein really liked to emphasize this, that in his experience, falsifying conjectures was really as very much as useful as discovering, because that would just save a lot of time rather than trying to prove something that really isn't true. We'd like to know that before we get started. Again, I don't know about you or any of you, but I personally find that I'm a lot more motivated to put the effort in to actually prove something if I've been convinced by long, hard work and experimentation that it really is true. And I think that there's something really to be said for that.
Okay, so another question is, are there a lot of cases where such eye tests as the crescent test are used?
Oh, very much, particularly when we look at some of these visualization techniques. If you look at that paper down below, visualization in several instances disclosed some facts that we had no idea were there just by looking at digits. And so again, they're very definitely visual aspect of this is I think even underplayed and understated at the present time.
Do you ever feel like using computer algorithms in mathematics is almost like cheating?
It is cheating. Oh, it's flat out cheating. We're discovering things that we do not deserve to know, but that's the way we make progress. And again, we have to remember that we again, finding numerical evidence may give us a lot of confidence, but we still have to prove things the old-fashioned way. But even there, I think having some intuition that we get from working out examples is very helpful.
How powerful a computer do you need to test enough cases? If my computer isn't powerful enough to run through bigger, more expensive cases, how can I continue?
Well, let me just mention my day job, you might say, where I spent most of my, a lot of my career is with was 15 years at NASA Ames Research Center and 15 years with the Lawrence Berkeley Laboratory in Berkeley. And in both of those cases, I was in the divisions that operated their supercomputer centers. And so I've had supercomputers at my disposal. But let me just tell you a secret here. Most of my research in experimental math, I've done just on laptops or workstations. And like my preferred platform is an Apple workstation. And so I'm the proud owner of a new Mac Studio, which is just sitting here, there, I touched it. And it works wonderful. And so a lot of really good computation can be done even with rather modest platforms.
You mentioned the Jonathan Borwein formula being proved for specific cases, x equals y equals 1 over s. Has it ever been disproved or expanded upon for more general cases? For example, x equals 1 over s and y equals q over s.
Okay. Jonathan Borwein's formula works for all x and y. But in the two-dimensional case, there is no equivalent known yet. I don't know of any equivalent for three-dimensional. But yeah, this allows us, this is not restricted to the x equal y equal 1 over s. This works for all x, all integers, or all real numbers, x and y, actually.
How do you find inexpensive algorithms? Are they cited in relevant papers, or do you have to develop them yourself?
This is a big, perhaps the central challenge of this business, is that because we have this need to compute things to hundreds and thousands of digits, we're really out on the left wing of numerical methods. Classic, the standard numerical analysis that we study in undergraduate courses, they just don't, they've never really done that. And so a lot of the schemes they discover really just are not appropriate for very high precision. So this is the central challenge of this business, is to find, or at least to sift through a lot of the known algorithms and find those that work at high precision well and those that don't.
Sambar, you've had your hand up for a while, so maybe you want to speak.
Oh, yeah, I just sent my question in the chat, but no problem. So my main question was that when can we, trust our vision or judgment so that we can convince ourselves that our proof or conjecture, that our conjecture is actually right? And, how would you train yourself to be able to make observations like that? Because I would have never been able to see by looking at the crescent that that's correct. I would not have been able to do that.
Well, this is the you might say the empirical aspect of doing this type of work, is that you just have to develop a lot of experience. You have to, not only from other papers, but from your own work. And you have to apply a lot of tests along the way of your own design. And say, let me test to make sure this is still holds. Let me test this. And sort of develop your own sense of what type of tests and conditions will give you a high level of confidence. I mean, like, for instance, when I first started doing these PSLQ developing this PSLQ algorithm with Ferguson, again, we would use it, and then we would say, well, let's do the following. We just discovered what we think is an identity, say using 200-digit arithmetic. Let's now calculate it to 400-digit arithmetic and see if the relation still holds. Oh, it does. Wonderful. Let's calculate it to 1,000 digits and let's see how it holds. So sort of a rule of thumb that's developed is, does the relation hold to significantly higher precision? And by significantly, we mean typically like 100 digits or more, beyond the level that was used to initially discover it. Then that's sort of a good, it's not a proof, but it's a very strong numerical evidence that you really do have something. And again, this thing about the crescent shape, that really, again, just sort of developed because I was just seeing all of the examples. And whenever I fixed many bugs in these codes. And inevitably, when the computation would fail or when a bug appeared, the way I would know it is that all of the coefficients would be roughly the same size. They were essentially like random numbers, the same size. And again, that's just the sort of intuitive tests, and you start understanding things intuitively, again, which is sort of the opposite of the way we like to reason in formal mathematics. But if it works, do it.
Okay, that makes sense. Thank you so much.
How do proofs for things like the John Borwein formula work?
Well, in his case, you mean this formula?
I guess so.
Or the formula for pi?
Oh, I don't know. Matthias, which one did you mean?
Let me just mention, say this formula for pi. It was actually Peter Borwein, that his brother, that after this was discovered numerically, Peter Borwein was one that found the proof.
Oh, he said not the one for pi, the other one.
Oh, the other one. This one, presumably. Yeah, anyway, well, in this case, because Jonathan and Peter Borwein had written a whole book. It was called, here it is, Pi in the AGM by Jonathan and Peter Borwein. And this was published back about 1980, I think. 1987. And in that, they had developed a whole theory of theta functions. And so when Jonathan Borwein saw this and he saw a connection to the theta functions, he knew exactly the way to go. In fact, these particular formulas are in this book. That's where they were written down. So chance follows people who have already done research and have a broad background in a number of different areas of mathematics. People like that have these broad backgrounds, or even in some cases like mathematical physics, they are the ones most likely to see these connections that other people might not.
So where can these identities be used?
Which identities? I guess the question.
Vincent, which ones did you mean?
Well, a lot of these things like this, these identities that we had from the C, D, and E integrals, these are right out of mathematical physics. And again, you might say, what good does it do to understand these? Because these give us connections to other arenas of mathematics. We see that really these integrals are connected with theories, say like the Riemann zeta function and there's really a lot of intuitive understanding of these things. This is why in fact, I'm most interested of all of the experimental math work I've done. That to me is the ones that make that are the most meaningful, those that have connections to mathematical physics and chemistry, because that really gives us a rooting in the real world.
If a computer gives you a strong indication that your hypothesis is true, can you rely 100% on the computer? Is that a legit proof? And vice versa, if a computer gives a strong indication that you were wrong, how do you know for sure that your hypothesis was wrong?
That is a very good question. Yes, computers are not infallible. Software has bugs. I've encountered them in every piece of software, not only, of course, many, many times in the software I've written myself, but even in things like Mathematica and Maple that are that are backed up by large staffs of people and millions or thousands of people around the world using them. yeah, I've encountered bugs. Software has bugs. It'll never be perfect. All you can do, it's sort of like this problem here with the sync functions. John Borwing's initial reaction is, oh, there's a bug in the software in Mathematica or whatever Maple, whatever they use to do these calculations, but it turns out not. But you know, bugs happen. So what you need to do is that if you get a result like this, try implementing it with some other tools or use some other tests. And like if both Mathematica and Maple give a result like this, well, then it's very likely true. It gives us just a lot more confidence that it really is true. And so again, I think John Borwing and I that wrote many papers along these lines, we would always use at least two different mathematical tools to check everything that we're doing.
How are computers used to assist with proofs? Do they just test cases, or can algorithms help with developing logical structures for the proof to follow? And as a follow-up, would it be possible for computers to generate proofs without human input?
Yes, is the answer. Yes, there's a whole new field of formal methods where software packages are put together that can allow you to prove some theorem right from basic axioms all the way, every single step, no hand waving, no, it is clear that, none of this. No, they literally gives a full, logically checkable proof. For instance, a colleague of mine, Hales, what's his name?
Thomas Kepler conjecture.
Thomas Hales, exactly. A good friend of mine. He was the one that first completed a proof. You've all been to the grocery store and seen oranges stacked in nice pyramidal, like pyramids patterns. And there's been a long conjecture going back to, let's see, who was the first to
probably Kepler. Kepler, right?
Kepler, I think, initially was the one that conjectured that way of stacking oranges is the most space efficient method possible. And no one had been able to prove that. And anyway, Tom Hales and another graduate student, who was actually my colleague Helaman Ferguson's son, Sam Ferguson, actually. Sam Ferguson and Tom Hales together did a computer-assisted proof of that fact. And again, this caused a bit of an uproar at the time, even made, I think, the New York Times, people debating whether Hales and Ferguson had really proved this or not, or whether because it was relying on computer computations. And so Hales and some students, bit by bit, entered this entire proof structure into one of these computerized logical proof checking programs, and it was able to verify it all the way. So yes, we have computer schemes that can discover results, and we have computer schemes that can very thoroughly logically check it right down to the very last step.
Why is it so much more computationally exhaustive to compute double and triple integrals rather than single integrals?
Well, we compute single integrals by sampling the function at, say, like 1,000 points, say, in one dimension. So if we're doing that in 2 dimensions, we've got to sample in 2 dimensions, which means like 1,000,000 points. And in 3 dimensions, that's like 1,000,000,000 points. And in 4 dimensions, it's trillion points, and so even if every one of those computations is very, very fast, in each one of those, we're evaluating a function that might involve like sines and cosines or who knows what. And so doing that billions and trillions of times is just expensive. There are certain schemes that can give us approximate values to like 5 or 6 digits, but the sort of things that we need, where we need hundreds of digits or more, that's really, there's no good way of doing that. I mean, that's a real fundamental, that would be a great research achievement if someone can find some way of doing that more rapidly than just simply sampling points in multiple dimensions.
Since modern mathematicians have the choice of relying heavily on advanced computational algorithms, is the way they prove problems different compared to the way used by mathematicians years ago? Would computational tools retain mathematicians' motivations to prove a problem from its origin?
Could you say that again? I didn't quite catch.
Just which part? All of it, or?
Well, start over. Let me.
Yeah, sure. Since modern mathematicians have the choice of relying heavily on advanced computational algorithms, is the way they prove problems different compared to the way used by mathematicians years ago? And would computational tools restrain mathematicians' motivation to prove a problem from its origin?
There has really been a sea change in the usage of computers. I remember back in the 1970s, that may give away how old I am. When I was a graduate student, I remember my advisor this is at Stanford University in Department of Math. And for my research or my dissertation work, I wanted to do some computational tests. And so I went to the administrative aides there at the department office, and I said, I'd like to apply for a computer account on the university's mainframe computer. And so they got back to me later, and I finally got my account and did my computations. But I later learned that was the first time any graduate student had ever requested in the math department had ever requested a computer account. And I still remember my advisor in chatting with a couple of his colleagues, and they mentioned some colleague or someone that they knew that was trying to do some computer calculations in their research. And they just talked about it in just the most derisive terms. I mean, it was very clear, real mathematicians don't compute. And nowadays, increasingly, I guess there are only 2 kinds of mathematicians: those that will admit to doing some computations to help get an intuition and guidance in their work, and liars. And it's really just been again, there are still the old guard that want to only work with pencil and paper and eschew any type of computation, but almost all of the younger crowd see this, and it really is giving a different sense because even if the nature of the process of proof has not really changed much, the process of exploration and gaining insight and intuition has dramatically changed in favor of using computers.
Are there alternatives to PSLQ that can achieve the same task in a smaller or equal time complexity? Is the LLL algorithm you mentioned slower than PSLQ, since you said PSLQ is the most widely used?
LLL is not really designed for this. It's designed to find short vectors in an integer lattice. And so to do it for integer relation algorithms, we have to convert our real vector into integers and then try to find that short vectors that would correspond to an integer relation. So it's not really designed for that, but I have heard some people are quite successful with it. One problem is that the LLL algorithm just itself is not really well documented and standardized as to what it is. I tried to actually code it up from one of their papers and just gave up. It's just not, it's just not very well documented. But on the other hand, I will grant perhaps there's something there. Maybe it can, if we can get that really working well, it could be faster than PSLQ. It may well be. That's a good project if you'd like to work on a project, sort that question out.
Okay, perhaps last question. What programming language or languages are considered the standard for complex mathematical computations?
Well, here are some I mentioned. Most people use C, some C++, some Java, some Python. I confess, I'm old school. I use Fortran, but Fortran is still the premier language for very high performance scientific computation. And a lot of packages they're targeted to Fortran code. At least, and there are a lot of advanced features. The modern Fortran standards includes a lot of object-oriented type of facilities, and you can basically anything you can do with C or C++, you can do in Fortran too. And so that's my personal preference. But again, I most of the younger mathematicians I know that are writing their own code. If they're not just using, you can write code in Mathematica and Maple if you want, but if you really want the best performance, you really in speed, you're really pressing the limits of computing, you probably want to write it in C or C++.
All right. Well, thank you for a wonderful talk and a very spirited discussion section. Yeah, so thank you.
Thank you very much. I mean, very interesting questions and feedback.
Okay, so now, okay, let me end this recording and start the next one.